Guys, welcome back. Day 17, I believe. 16, 17, I don't know. Today we're going to be doing another NeetCode problem. Two integer sum. And they want us to have a log. Time complexity of bigger 1. So basically one operation. Given an array of integers, numbers, sorted in non-decreasing. So that would mean that numbers are going to be ascending. Right? Given an array of integers, numbers, as sorted, basically, return the indices. So one index of two numbers, index 1, index 2, in a list, such that they add up to give a target number, and that index 1 is less than index 2. So index 1 and index 2 cannot be equal, therefore you may not use the set elements. So okay, I have an idea. Okay, so got that. So listen, integers. Okay. So this trick I want to use is I start at the number. That number is, since it's over, we can just go from that point backwards and check. So doesn't make that much sense at first glance, but it will. So let's say we have a target as 3. So target is 3. Then we'll find index where it's equal or less than 3. If we can't find something that's equal to 3, probably go larger. It's actually determine it's less than 3. So let's say we have a target of 3, like we said, so target. So I'm going to do negative stuff. pointers.
Let's solve LeetCode 167 TwoSum II. So we're given an input array that's already sorted in ascending order, and we want to find two numbers that sum up to some target that we're also given. So in this case, the target is 9. The two numbers that sum up to 9 in this array are 2 and 7. And we want to return the indices of these two values, but the catch here is that the indexes are 1 based. They're not 0 based, so the first element has index 1, the second element has index 2. I don't know why exactly they did that in this problem. It's kind of weird, but they did for some reason. We're also guaranteed that there's exactly one solution and we can't use the same number twice. So in this example that they gave us, the two first numbers sum up to the target. So that's not really a good example. So I'm going to look at my example over here that I drew. So the first idea that might come to your mind is just look at every single combination of two numbers. So let's say we're starting at the first number 1. Let's look at every number combined with 1 and see if it can sum up to the target 9. So first we check 1 plus 3. That is 4, so it's not 9. Then we check 1 plus 4, that's 5. Then we check 1 plus 5, that's 6. 1 plus 7 is 8. And 1 plus 10 is 11. So now we've gotten to the point where at 1 plus 10. But the interesting thing about this is the first combination that's greater than our target 9. So do we have to keep looking at the next element? Since we know the array is already sorted, there's no number that's going to come after 10 that's going to be added to 1 that could possibly sum to the target 9. So since 1 plus 10 is already greater than the target, we don't have to look at the remainder of the array because there's no number that could possibly come after 10 added to 1 that would ever be the target. Every number is going to be greater than the target, so we don't have to consider 11 anymore. So we basically remove it from consideration from our array. So we didn't find the two numbers that sum to the target. So now let's try if there's any combination with 3 that could possibly sum to 9. So we start at 4. So 3 plus 4 is 7. 3 plus 5 is 8. 3 plus 7 is 10. So this is the first combination. 3 plus 7, which is 10, is greater than the target 9. So we don't have to look at any number that comes after 7 because we know that it will never equal the target. So we can basically say, well, 10 is removed from consideration. We don't even have to look at it. So we couldn't find a combination with 3 that could sum to the target 9. So now let's check the next number, 4. The first number is eliminating elements from the end of the array in reverse order. Can we use this to our advantage? This is basically the intuition. Remember, this array is sorted. We can use that to our advantage. So let's try the exact same problem with a slightly different algorithm using what we just learned. Our target is still 9. Since we're eliminating elements from the end of the array, we can use 2 pointers. One pointer is going to be at the beginning, or a left pointer. One pointer is going to be at the end, or the right pointer. So we currently have a 1 and an 11. Let's add these together. 1 plus 11 is equal to 12. So that's greater than our target of 9, remember? So since this target is too big, we need to decrease it. We have a choice of which pointer to shift. If we shift our left pointer here to 3, we're going to be increasing the sum. We don't want to do that since the sum is already too big. So instead, let's take our right pointer and shift it to the left. Now we've decreased the total sum, so let's recompute it. 1 plus 7. Now it's 8. This is too small. We decreased our sum too much, so now we need to increase it. So since the array is sorted, we can take our left pointer and shift it to the right to increase our total sum. Now we've increased our sum, so it's now 3 plus 7. But we went too far again. Right now it's too big again. It's bigger than 9. So what do we have to do this time? Well, we want to decrease our sum, so we're going to take the right pointer and shift it left. So now we decreased our sum. Let's recompute it. 3 plus 5, but that's 8. So again, we got to 8. It's too small again, but we're guaranteed a solution, so we're going to keep looking. Since our sum is too small, we're going to increase it by taking our left pointer and shifting it right. Now we can't really shift our pointers anymore, so we better be at the right solution. Let's check. 4 plus 5, that's exactly 9. So we got our target. And so we want to return the indices of these, which are going to be 3 and 4, right? In this case, we don't have to iterate through the entire array more than once, and these left and right pointers are never going to cross each other. We don't need extra memory either, so our time complexity in the worst case is big O of n. We found a linear algorithm using 2 pointers to solve this problem. We didn't even need extra memory. Now we're ready to code up the solution. So we remember we have 2 pointers left and right. The left pointer is going to be at the beginning of the array, so index 0. The right pointer is going to be at the last index, so length of numbers minus 1. And we need a loop to iterate through our array. The condition in this case is left is less than right, but it doesn't really matter because we're guaranteed a solution, so we're going to return a solution no matter what. So like we just did in the example, let's compute the current sum. And we remember if our current sum is too big, so if it's greater than the target, we can decrease our sum by taking our right pointer and shifting it to the left. On the other hand, if the current sum is too small, we want to increase our sum by taking the left pointer and shifting it to the right. The last case is that our current sum is exactly equal to the target. In that case, we want to return the indices left and right. But remember, they're based on 1, so we're going to add 1 to each of them. We can put a return out here, but it's not needed because we're guaranteed a solution, so our loop will return the solution. And it works perfectly, a linear time algorithm with no extra space. Make sure to like if this was helpful and subscribe if you want more.